Imagine for a moment the sound of your own home. Maybe it's the quiet hum of an appliance, the creak of floorboards, or just, the gentle stillness of a lazy afternoon. Now, have you ever really stopped to consider what's happening in that unseen world just inches beneath your feet, right under those floorboards? For millions of us, that hidden space is far more active and far more critical than we might realize.
It really is. It's a fundamental part of our homes that's often out of sight, out of mind, but which has, well, a profound impact. Today, we're taking a deep dive into suspended timber floor voids, especially common in older homes. And this isn't just empty space. It's a dynamic environment with significant, often surprising implications for your home and, importantly, your health.
Okay, so our mission today is to unpack a stack of fascinating sources. We've got research papers, building regs, case studies, practical guides, all focused on truly understanding these voids. We'll explore the hidden problems they cause and, crucially, some surprising solutions that are emerging. I'm really eager to see what we uncover here.
And you should definitely care. We're going to explore why this matters for your energy bills, your everyday comfort, and perhaps most importantly, your health. The insights we share today might just completely change how you perceive the very ground you walk on inside your home.
Okay, let's dive in then. In your notes, you mentioned the historical context. How far back does this go, and how common are these floors today? Because these aren't just old floors, they're really part of our architectural history, aren't they?
That's a great starting point, yeah. Understanding the origins helps grasp the modern challenges. So, suspended timber floors, they really became the dominant construction method here in the UK, starting way back in the 18th century. They were a huge leap forward from, just compacted earth floors, offered much better conditions. Today, we're talking about approximately 10 million UK homes that still have these floors.
10 million, wow.
Yeah, and around 5 million of those homes were built before 1919. So, really old housing stock.
So a huge segment of our homes. You'd think such a common design would be pretty sorted out by now. What was the original idea? Why have that void space?
Well, historically, these voids, they served several vital purposes. They allowed ground moisture to dissipate naturally, which was crucial. They also made it easier to build on uneven ground without massive earthworks.
Okay.
And they provided fresh air for, say, fireplaces or stoves, and helped moisture evaporate from the walls below the floor level, too. For its time, it was actually a very clever practical system.
That does sound quite ingenious. But if we fast forward to today, what do our sources say about the current state of these voids? Are they still doing that good work, or has something gone wrong?
Yeah, unfortunately, the reality now is often quite different. Our sources frequently describe this void as get this, cold, infested, damp, and moldy petri dish.
A petri dish? That doesn't sound good.
Not at all. It's commonly found with standing water and really high relative humidity, or RH. We're talking often between 60% and even 95%.
Okay, so petri dish sounds worrying. What specific conditions in that dark, damp space make it so problematic? What happens at those high humidity levels you mentioned?
Well, what's really critical here is that the conditions for pretty significant problems are almost always met down there. Mold growth, for instance, can start at just 70% RH in these voids. But maybe even more concerning for the actual structure of your home, timber rot can begin at 90% RH if it's around 10 degrees C. And sometimes it can even start below 80% RH if the temperatures are a bit warmer.
Right.
So what was once a helpful space can quickly become a serious liability, just silently undermining your home structure.
And it's not just about what might be growing down there, is it? I remember growing up in an old house, and we always blamed the windows for drafts. Never thought about the floor. Our sources say older homes can lose a surprising amount of heat through these floors. How much are we talking?
It's a huge factor both for comfort and energy bills. Older homes can lose up to 1/3 of their heat just straight through these uninsulated suspended timber floors.
A third. That's massive.
It is. It means you're constantly battling heat loss, basically just vanishing into the ground. Your heating system has to work so much harder, and it costs you more.
So, to really get my head around this, we're talking about a big chunk of our home's ventilation being completely uncontrolled, almost like a hidden, permanent draft.
Precisely. Air infiltration, air leaking up from that subfloor void, can actually contribute up to 54% of the uncontrolled ventilation in a house.
54%.
Yeah, and that translates directly to those uncomfortable drafts you feel, especially around your feet, which naturally makes you turn up the thermostat, right?
Yeah.
Using even more energy. And then to add insult to injury, if you've got uninsulated pipes running through that void central heating pipes, for example, They can lose up to 10% of your boiler's heat just radiating into that cold, damp space.
Wow. It's just wasted heat.
It's a constant drain, exactly.
So this isn't some abstract building science issue. It directly hits your comfort, your wallet, your daily life. And you might never even guess the floor's the main culprit. That's really eye-opening.
It is. And the problems, unfortunately, don't stop with just drafts and heat loss. This leads us into the invisible health hazards lurking below. What's fascinating here, and quite concerning, is that the problem isn't just stuck in the void. It actively migrates up into your living space. It becomes a critical health concern.
Okay, so you're saying this damp, humid air from the void doesn't just stay down there. It actually comes up and affects our rooms.
Absolutely. High humidity in the floor void directly raises the moisture content of the timber joists, the floorboards above, everything. That dramatically increases the risk of mold, rot, and eventually even potential structural failure. And as you suspected, this humid air doesn't stay put. It finds its way up through gaps in floorboards, around pipes, edges of the room,
Right.
and it infiltrates your living spaces, raising your indoor relative humidity. This, in turn, significantly increases the risk of condensation, damp patches, and mold growth inside your home, not just hidden away below.
So these floors could essentially be pumping unhealthy air directly into our homes. What kind of invisible invaders are we actually dealing with here? What's in that air?
It's a very serious point. Air infiltration from these floor voids creates what some of our sources call invisible health hazards.
Ugh.
Studies have actually found that these voids can harbor 10 times more mold spores than the occupied indoor spaces right above them.
10 times more.
Yeah. These fungal spores, along with other microbes and bacteria, are then literally carried up into your living environment by the airflow. We're also talking about something called microbial volatile organic compounds, or MVOCs. These are gases produced by the fungi and microbes thriving in these damp conditions. And these MVOCs can seriously affect human health, often before you even see any visible signs of mold or damp. So occupant health can be profoundly affected by these airborne contaminants.
Okay, here's where it gets really interesting and honestly a little unnerving. We often try to improve our homes, right? Make them more energy efficient. But our sources suggest that if we don't understand this whole floor void system, we could actually make things worse. How does that happen?
This is such a crucial point, a real aha moment from the deep dive. When you're retrofitting for energy efficiency, maybe adding insulation elsewhere or improving windows, if you just increase extract ventilation in your home, like put in the powerful bathroom or kitchen fans, without making the ground floor airtight first, you can actually increase the amount of air being pulled up from the floor void. You create more suction, essentially. This means you're actively drawing more excess humidity and more contaminants into your home, especially in winter because of something called the stack effect.
The stack effect.
Yeah, warm air rising in your house creates lower pressure at the bottom, which literally sucks colder air and whatever's in it up from the void through any gaps in the floor.
So our good intentions to make our homes more energy efficient could backfire and actually make the air quality worse if we don't tackle the floor void first.
Precisely. Some research even suggests that certain ventilation systems designed to slightly depressurize a home, like some mechanical extract systems, could pose a potential health risk exactly because of this increased transfer of fungal spores from crawl spaces. It's a critical, often completely overlooked, interaction when you're trying to improve your home's airtightness and ventilation.
Okay, so given all these problems, what have people traditionally done about this hidden world? If anything, there must be some existing ways people try to deal with floor void moisture.
Yeah, people have definitely tried things over the years. One common approach is covering the ground below the floor with an impermeable barrier, like a heavy polythene sheet, trying to stop the moisture rising. Another method, apparently quite popular in the Netherlands, is backfilling the entire void with sand.
Sand? Really?
Yeah, and some go even further, ripping out the whole suspended timber floor and replacing it with a solid concrete slab.
Right, okay.
And what's the verdict on these traditional methods?
Well, the sources seem to agree. None of the above are simple or cheap. And they all have pretty significant shortcomings. They often involve massive disruption, high costs, and sometimes they don't fully solve the underlying issues of moisture movement and air leakage in the long run.
And when it comes to just trying to insulate these floors traditionally, what our sources describe sounds like, well, a real pain.
It truly is. The standard process is incredibly complicated and very labor-intensive. You're typically looking at emptying the room, taking up carpets, maybe underlay, and then lifting all the floorboards. That alone is a huge job.
Yep.
Then you might have to fit supporting nets between the joists or maybe an airtight membrane, carefully taping and sealing all the joints. Then you have to hand cut insulation, like mineral wool rolls, to fit snugly between every single joist. Think of the fiddly work and the waste from offcuts. And
Ah,
then finally, you have to put everything back: floorboards, carpets, furniture.
that sounds like weeks of disruption, dust everywhere, and probably a massive bill.
Exactly. It is disruptive, it's expensive, often 10,000 pounds or even more, depending on the house, and it can easily take up to 2 weeks per room, as you say. Plus, it generates significant landfill waste from offcuts and potentially damaged boards. There's embedded carbon in making new materials if needed, and honestly, there can even be risks for the workers operating in those sometimes cramped, dusty voids. But here's the kicker. Critically, these traditional methods often perform really poorly in reality. Payback periods can exceed 50 years.
Years.
Yeah, and studies have shown many installations fail to deliver the energy savings predicted by models. Some deliver no measurable savings at all, and others are way down, like below 5%.
Wow, so all that disruption and cost for potentially very little gain. And here's another crucial point our sources highlighted, which seems almost counterintuitive. Vapor open insulation. Things like glass wool, mineral wool, or maybe open cell spray foam.
Hmm.
It actually does not protect the timber floor from moisture. Why is that? This is another really key insight, yes. Studies have actually found mold growing on vapor, permeable insulation itself, and on the adjacent timber joists and the underside of floor decks, sometimes within just a year of installation.
Even with insulation installed.
Yes, because these materials, being vapor open or breathable, by their very nature, allow water vapor to pass through them. So moisture from the damp void air migrates into the insulation and right up against the colder timber surfaces the joists, the floorboards. It basically acts as a pathway for moisture, trapping it right where you don't want it, rather than keeping the timber dry.
Okay, so if traditional methods are disruptive and often ineffective, and vapor open insulation can actually trap moisture, what does work? What did our deep dive reveal as the criteria for an effective solution down there?
Right. Our sources point towards a solution that needs to meet several quite stringent criteria all at once. For an insulation layer to genuinely solve the problems, it really must be 1. Airtight to stop that contaminated air infiltration. 2. Vapor impermeable to actually block the water vapor from the void getting to the timber. 3. It needs to fully encase all the structural elements, leaving no gaps. And 4, it needs to be highly insulative, obviously, to reduce heat loss, but also importantly, to keep the wood itself warmer and therefore drier.
So it's tackling all those things: air leakage, vapor, heat loss, cold timber simultaneously.
Exactly. You need to address all 4 to really crack it.
And this is where closed cell spray polyurethane foam, or SDF, underfloor insulation UFI, comes into the picture. It sounds like it's identified as one of the key options that can meet all these tough criteria. How does it specifically hit those core problems?
Precisely. Closed-cell SPF UFI seems uniquely suited to addressing those core problems together. Because it's sprayed on and extends, it creates a completely seamless, airtight seal. This dramatically lowers humidity right at the wood surface, leading to drier timbers and a much lower risk of mold and rot.
Okay, airtightness and drier wood, got it.
It also makes the entire floor structure significantly more airtight overall, which directly reduces that microbial risk, fewer spores getting drawn upwards. And crucially, closed cell foam is highly vapor impermeable. It acts as a barrier to water vapor, so far less moisture from the void can actually get through to the timber or into the room above, which, somewhat counterintuitively perhaps, leads to lower indoor relative humidity in the house.
That's a significant claim: lower indoor humidity. What kind of data actually backs up the impact of this type of impermeable insulation, both for, energy and health?
Yeah, the data presented in the sources is quite compelling. There was a 10-home study mentioned which showed that installing closed-cell SPF UFI decreased the indoor relative humidity by an average of 6%.
6% reduction, that's noticeable.
It is, and importantly, this reduction was still there, consistently maintained, a full year after the installation. What was also fascinating, and maybe a bit unexpected, was that the relative humidity in the void itself also dropped after the installation.
Really? How does that work?
Well, the thinking is that by creating such an effective seal over the ground and walls, it reduced the amount of moisture evaporating from the ground into the void in the first place. And critically, the study found that with these properly sealed airtight floors, no fungal spore transfer was observed from the void into the living spaces above.
That's huge for health.
Absolutely. If we connect this to the bigger picture, It really suggests it's about creating a genuinely healthier indoor environment, not just one that maybe feels a bit warmer because the drafts are gone.
And the energy savings. Many people are desperately looking for real ways to cut their bills right now. How does this SPF UFI stack up against other common insulation measures?
The energy savings reported are very significant and, importantly, seem consistent. Closed-cell SPF UFI reliably creates that airtight barrier, and studies show it reduces heat loss through the floor by up to 24%.
Up to 24%.
Okay? Now compare that to traditional underfloor insulation methods we discussed, which often deliver little, if any, measurable savings in practice. Or even loft insulation. Other studies suggest that often delivers below 2% long-term savings despite initial models. Cavity wall insulation, too, often shows an initial drop, maybe 7%, but that tends to fall back to below 2% over time as well.
So this floor insulation potentially outperforms loft and cavity wall in real-world savings?
Based on the data presented, yes, it seems to offer more substantial and sustained savings. The sources also mention that combining SPF UFI with heat pumps can lead to even higher winter heating bill savings averaging around 30%, with some months hitting 40%.
Why is that?
Partly because it reduces temperature stratification, cold air pooling at floor level, meaning the heat pump doesn't have to work quite as hard to maintain comfort.
Right. So these are tangible long-term savings that seem to consistently outperform other common energy efficiency measures. That's a powerful combination: better comfort, better health, and lower bills.
It certainly appears that way from the evidence we looked at. And beyond those obvious benefits of warmth and energy saving, there are other really crucial considerations that our deep dive uncovered,
Yeah.
things people might not even think about. Let's talk about radon gas, for instance.
Ah, yes, radon, colorless, odorless, dangerous.
Exactly. It's linked to about 1,100 lung cancer deaths every year just in the UK. And it's naturally occurring, drawn up into our homes from the ground, often through these underfloor spaces. Now here's the critical point. As we make our buildings more airtight through energy-efficient retrofits, sealing up drafts, we can actually increase the concentration of radon inside if it's present. We trap it in.
Oh, right. So trying to save energy could inadvertently concentrate a deadly gas. That's a really scary thought. How does the closed-cell SPF UFI address this?
It's a very important point. The good news is that closed-cell SPF, because it forms that continuous impermeable barrier, also acts as an effective radon barrier. Studies show it can reduce radon concentrations by between 68% and 98%, especially when it's combined with ensuring the void itself remains well ventilated to the outside air.
Okay, so it's not just insulating, it's actively protecting against a serious invisible threat that other energy measures might actually worsen.
Correct. It tackles multiple problems simultaneously.
And sticking with safety, fire is always a concern when people talk about foam insulation. What's the story with fire safety compliance for this type of underfloor insulation?
Yeah, that's a common question. It's important to reassure listeners that sprayable polyurethane foam UFI, when installed on the ground floor, is fully compliant with UK fire regulations. The SPF itself doesn't make the floor structure flammable. Remember, suspended timber floors are inherently combustible anyway, being made of wood.
Good point.
But the closed-cell SPF used for this application is specifically formulated to be self-extinguishing. It won't sustain a flame on its own.
Okay, that's reassuring. Now, this brings us to a really crucial distinction our sources highlighted, one that seems to clear up a lot of confusion and maybe bad press around spray foam. Why SPF under the floor, UFI, is different and much less problematic than SPF applied directly to the underside of a roof in a loft. So what does this all mean? It sounds like understanding where and how this stuff is applied is absolutely vital. It's definitely not a one-size-fits-all solution, is it?
Exactly right. It's all about the context. With underfloor insulation, the timber structure, the joists, the floorboards, is placed inside the insulated envelope. It's on the warm side. This keeps the timber warm and, crucially, dry, putting it at a much lower risk for moisture. It's protected by the insulation.
Okay, warm side, protected. Makes sense.
In contrast, when SPF is sprayed directly onto the underside of roof tiles or felt in a loft, it can place the roof timbers in the cold outside the insulated layer. This requires very specific ventilation strategies above the foam to manage moisture. It can potentially hide roof leaks until major damage occurs, and it has, as you know, unfortunately led to issues with mortgage lenders because surveyors can't easily inspect the roof structure underneath.
Ah, I see. Completely different situation.
Completely different. The application, the location relative to the structure, the moisture dynamics, it's all different. Understanding that difference is absolutely key.
That's a great clarification. Now, thinking about the bigger picture, sustainability. What advantages does SPF UFI offer on that front?
Well, from installation right through to end of life, SPF UFI seems to offer some notable advantages according to our sources. During installation, because it's sprayed directly and expands to fit, there's minimal waste. No offcuts like you get with rigid boards or wool insulation. Material is basically used only exactly where it's needed. And critically, as we mentioned, the carpets, underlay, and original floorboards usually remain completely in place.
Which means less stuff going to landfill.
Exactly. A huge reduction in landfill waste compared to ripping everything out.
Mm.
And you avoid the embedded carbon involved in manufacturing and transporting replacement flooring materials.
So less disruption, less waste, and better for the environment in that sense.
Absolutely. And then, over its life cycle, the installed SPF is inert. It doesn't degrade or release anything harmful. It's also very durable, expected to last the life of the building. Plus, by keeping the timber drier and warmer, it actually helps improve the life expectancy of the existing floor structure, reducing the risk of rot and insect infestation. It also significantly reduces thermal bridging those points, like joist ends, where heat can easily bypass insulation. SPF covers everything seamlessly.
And what about disposal, eventually?
Even at the end of a building's life, PU foam waste isn't just landfill fodder. It can be reprocessed into new products like high-density boards. It can be chemically recycled back into its constituent polyols to make new foam, or it can be used for energy recovery through incineration. So there are circular options.
Right. It sounds like a well-rounded solution from that perspective, too. Okay, let's get practical for listeners. How do I, as a homeowner, figure out if I even have one of these suspended timber floors we've been talking about? What are the clues?
Yeah, good question. There are usually a few simple cues you can look for. First, walk across your ground floor. Do the floorboards give a slightly hollow thud, and maybe even a slight vibration when you stamp on them? That's different from the solid feel of concrete.
Okay, the stamp test.
The stamp test, yeah. You might also see visible floor nails, especially in older properties where the boards are exposed or under thinner coverings. Look outside at your external walls, near ground level. Do you see small vents, often fitted with terracotta or plastic grills? These are air bricks, designed to ventilate the void. That's usually a dead giveaway.
Air bricks. Got it.
And generally, these floors are typically found in homes with other traditional construction features, things like solid brick walls rather than cavity walls, or chimney breasts. If your house has those, chances are higher you have suspended timber floors on the ground floor.
Okay, those are helpful clues. And if someone does have this type of floor and is considering SPF UFI, what's the installation process actually like? I imagine it's pretty high-tech if it's getting into these awkward voids, possibly with robots.
It is quite advanced, yes. It typically starts with a very thorough technical survey. Someone comes out to assess the void properly, check the depth, look at the existing ventilation, assess the condition of the timber, and map out any services like pipes or wiring that run through the space.
So they know exactly what they're dealing with.
Exactly. Then the actual SPF UFI installation is often delivered remotely. They might use a robotic system that crawls into the void and sprays the foam accurately onto the underside of the floorboards and around the joists. This is usually done within a single day for an average house.
One day. That's fast.
Much faster than the traditional methods. And during the installation, they usually keep the void under negative pressurization, basically using fans to draw air out of the void to the outside to ensure no dust or spray particles can escape into the house.
And the big plus for the homeowner.
The big plus is that occupants can often remain completely undisturbed in the house while the installation happens underneath them. It's a far, far cry from the disruptive, weeks-long process of traditional insulation methods.
Definitely sounds less painful. Now, this raises an important question, though, something you talked on earlier. Why do some common misconceptions about these voids and how to manage them persist? And how critical is it that we actually understand the real physics of moisture and air movement in our homes?
It's incredibly important, and yes, misconceptions are common.
Okay, here's one I've definitely heard. The idea that air coming up from a cold, damp void will automatically become less humid just because it warms up inside the house.
That sounds logical on the surface, right?
Right.
Warmer air holds more moisture, so the relative humidity drops.
It sounds logical, but it's a dangerous oversimplification. Yes, the relative humidity, RH, will drop as the air warms up, but let's say the void air is at 10 degrees C and 90% RH. If that leaks into your house and warms to 20 degrees C, the RH might drop to around 50%. But the absolute amount of water vapor in that air hasn't changed. You're still adding significantly moist air to your indoor environment.
And crucially, cold outside air Even if it's foggy or raining and seems damp, high RH, almost always contains less absolute water vapor than the air in a typical cool, damp floor void. So, ventilating your house with fresh outside air is usually better for managing indoor humidity than letting damp void air leak in. The void air might feel less damp once warmed, but it's still adding a lot of moisture overall.
Right, it's the absolute moisture content that matters for things like condensation and mold risk indoors.
Precisely.
Okay, and another big one. The common practice, or maybe temptation, to block up those air bricks in the external walls during winter, thinking it'll stop cold drafts getting into the void and keep it drier or warmer. Does that work?
That's a really, really bad idea, unfortunately, though you can see the logic people might follow. Blocking those vents actually does the opposite of keeping the void dry. It increases the void humidity because moisture evaporating from the ground gets trapped.
Traps the moisture.
Yes. And that increased humidity down there leads to increased moisture levels in the surrounding walls, particularly the external walls. Damp walls conduct heat much better than dry walls, so it actually reduces their thermal resistance and increases heat loss from your house.
So blocking vents makes your house colder and lose more heat?
Counterintuitively, yes, in the long run. And maybe more importantly, it promotes mold growth, both in the void and often indoors at low levels like behind furniture near the floor, where that trapped, humid, stagnant void air is slowly seeping up.
Wow. So the absolute key takeaway here is that adequate, continuous ventilation of the floor void itself to the outside air is crucial. It's vital for the health of the building structure and for the health of the people living inside. Interfering with that based on misunderstandings can have some pretty significant negative consequences.
Precisely. It really underscores the need to understand how these systems work and to apply solutions like appropriate insulation that work with the physics of the building, not against it.
We have journeyed deep into the hidden world beneath our homes today, haven't we? We've uncovered the historical context, the quite pervasive problems of damp, mold, heat loss, and even radon that lurk in suspended timber floor voids. And we've explored how a modern, engineered solution like closed-cell SPF UFI seems capable of delivering really significant benefits for health, for energy efficiency, and for the overall longevity of the home itself. It's a testament to how these seemingly small, unseen spaces can have such enormous impacts.
It really is, and it highlights how critical it is to apply the right solutions based on sound building science and evidence rather than just assumptions or outdated practices.
Exactly. So it leaves me thinking, considering these invisible health hazards and the significant, often underestimated heat loss from our floors, what other unexamined areas of our homes might be silently impacting our health and our wallets without us even knowing? How